So today we're joined by Dr. Krenn, who's calling in today from Erlangen in Germany, from the Max Planck Institute for the Science of Light. And he'll be talking today about towards an artificial muse for new ideas in science. So whenever you're ready, please feel free to get started.
Yes, thank you very much. Thanks for inviting me. My name is Krenn. I'm a research group leader here at the Max Planck Institute for the Science of Light. And the idea of my group is to see how we can use computers at a more conceptual level in science, especially in physics. And to do this mainly in two different directions. The first one is we use AI to design new physics experiments. And when they find some experiments that are beyond the quality of human experiments, then we know there are some tricks or ideas inside that we as humans probably don't know. And then we can look into those solutions and try to understand what the machine has discovered. And the second branch is using huge amount of scientific literature to come up with new, personalized, impactful, hopefully interesting research ideas. And I will start with the first part, and then in the end, talk about this topic at a bigger picture. Okay, so if you think about the question of designing experiments, I like to think about it as the enormously large search space of all possible experiments. So imagine a space of all possible experiments that you could build. So most of those experiments are completely useless. They have no meaning. They cannot measure anything useful. But some of those points have very exceptional and useful and interesting properties. And our goal is to find those points in this large search space. And just to give you an example of some numbers, if you just have 3 lasers, 3 beam splitters, and 3 detectors, you can already build up more than 1,000 different combinations of experiments that you could build. If you have 5 of each of those, you can already build up more than 80,000 different combinations. And that doesn't even include the continuous parameters. These are only the topological combinations that you could build. And this space has for a long time been investigated by creative and experienced human researchers. And they have found actually many exciting experiments, obviously. So for instance, here we could have some gravitational wave detectors. This could be some fancy super resolution microscopes. This could be some, I don't know, high energy physics experiments. But in general, it's kind of unlikely that we have already found the all exciting experiments with which we can observe the universe. And that is exactly where artificial intelligence and automated experiment designs come in. Such programs can explore this space in a very different way than human can do. And by that can hopefully help us to find new experiments that we can use then to observe the largest and the smallest parts of the universe. So for me, this has started during my PhD a little bit more than 10 years ago. So I was working in an experimental quantum optics group, in the group of Anton Zeilinger. And in this group, we wanted to explore the property of quantum entanglement. So quantum entanglement happens when 2 particles can share a property, and when you bring those particles away from each other, they still in some way share this property, even without, even if the distance that they are away from each other is very, very large. So let me explain the simplest form of entanglement. So imagine you have 2 photons, two light particles. And those two light particles can have a color. For instance, they can be red or they can be green. And imagine that you can create now a state where both particles are red or both particles are green. And you can create the state in such a way that before the measurement, you don't know whether the particles, whether the photons are red or green. And only when you measure one of the two particles, it takes its color, for instance, red, and then at that moment, its partner particle is also red. And the interesting thing is that this is not only that you don't know, but actually what is happening is that there's no information anywhere in the universe that tells you whether those particles are red or green before you measure them. And even more strangely, this can happen even if you separate those particles over very large distances. So now imagine you have a state like this, where the two particles are both either red or green, but don't have a well-defined color before you measure them. And then when you measure one of them and you see it's green, its partner particle, which can be kilometers or hundreds of kilometers away, also gets the color green. But this is a very strange behavior of quantum physics. And in the lab of Anton Zeilinger, we wanted to explore this and more complex forms of quantum entanglement. So we wanted to go to more complex systems. So there are basically two ways to go to more complex systems. One way is to increase the number of particles. Now, instead of two photons, I can have three photons, where all of the three photons are red, or all of the three photons are green. And again, before you measure them, they don't have a well-defined color. And only when you measure one of them and you see it's red, also its two partner particles are red. And again, that works even if you bring those particles at very different locations, very far away from each other. So this is called multi-particle entanglement, and this is very important for quantum computing. So quantum computers need many highly entangled particles. A different way to increase the complexity of entanglement is by having more than two colors. Now imagine we have our two photons, and those two photons can both be red, or both be green, or both be blue. And again, the same thing happens. Before you measure them, they don't have a well-defined color, and only when you measure one of them, and let's say it's blue, then its partner particle is also blue. And with this, this is called high-dimensional entanglement, and this is used quite a bit in quantum communication, which is a new form of communication that is based on the laws of quantum physics, where you can do, for instance, fundamentally secure communication and key distribution and so on. High-dimensional entanglement is a lot used there because you have now more, you can store in a way more than one bit or quantum bit of information per photon pair. And that's very useful for communication reasons. So both of those forms to increase the size of the entanglement have been observed experimentally in the late 1990s or early 2000s. During my PhD, we wanted to go beyond this and observe quantum states where you have more than two particles entangled in more than two colors. So for instance, we wanted to generate a state like this where you have three particles, where all of the three particles are either red or green or blue. And at the time, not only experimentally, this has never been observed before, but there were even theoretical questions about the structure of entanglement and how it behaves and what you can do with it for such states. So we were very excited and wanted to generate the states and measure some of the properties that have never been measured before. So now usually how that works is when you want to create a state and or create a quantum system and observe it, you need to find a experimental setup that you can put in the lab and that produces what you want. And usually how that works is, in that community at least, is that some experienced people go to a blackboard or go to a piece of paper and they doodle around, and quite quickly, usually one finds a way how one can implement the specific states in the laboratory with the equipment that one has in the laboratory. So that was the state of the art until my PhD. So usually all of those experiments have been designed by clever humans. And we tried the same. We wanted to build the state, so we wanted to find the experiment that can create it. And then we sit together, and after a few hours, we still didn't have any solution how we could build it. And then a few days passed by, and we still didn't have any solution. A few weeks passed by, and we still didn't have a solution. And then after a few months, I think after 2 or 3 months, I thought, okay, that is very weird. It's crazy that we cannot find a solution. Maybe either there's a fundamental problem, or we as humans are just not very good to find this solution. So I wrote a computer program, a quite simple computer program that basically has all of the optical equipment that we have in the laboratory, has in the toolbox, and can use that to set up virtual experiments and compute the outcome of those virtual experiments. And the program had a small learning routine such that when it finds some non-trivial experiments, it stores those, even if they don't satisfy the final goal. If they're non-trivial, it stores those into its own toolbox, so it can easily reuse it later again. So I wrote this algorithm, and I started it in the evening, and in the morning, I found a solution.txt file at my desktop. And I was very happy about this, and I was very excited. We looked then into the solution.txt file, and after 1 day, roughly, we convinced ourselves that this file shows exactly the solution that we wanted to find for the last couple of months. So we were extremely excited that a machine can solve a question for experimental design that we as experts were not able to solve. And that solution was even practical feasible. So we were able to build it in the laboratory. And actually one of my colleagues, mainly Manuel Erhard, was able to build this state in the laboratory and observe some of its properties for the very first time. It only took 4 years between finding the solution and getting the experiment to work. So, okay, it was quite an effort, but it was possible to observe those phenomena for the first time. So obviously we were very excited and tried to apply this technique also to other topics that we were not able to solve. And we solved several of those other questions we couldn't come up by ourselves. But for me, the most interesting thing was that one can actually learn something from those solutions. So that happened when I took this question about finding this specific quantum state and asked the program a much more general question. A question about, give me non-trivial, high-dimensional, multi-particle entangled states, or experiments that produce those states. Because it was basically completely unknown, this field was completely unknown at the experimental level. So I wrote this program, and I extended this program. And what I had to do is I had to give the program some constraints, some resource constraints, because it is known that computing large quantum systems becomes extremely time consuming and classical computers. So if I don't give any constraints, it would probably just find only solutions and get stopped in endless loops, because it it is so expensive to compute. So I had to give some constraints. And with those constraints, I knew that the program cannot find any solution larger than a specific level of entanglement. So I knew it's not possible to find any entangled state larger than 9 dimensions. And then after a few days, when I came back and looked at the results, I saw the program found a 12-dimensional entangled system. And when I saw this, I immediately knew my program has a bug, because that is usually how a bug announces itself. It does something that is actually impossible. But I analyzed the solution, and the solution was perfectly fine. I was able to compute the solution that the computer found just by hand and confirmed that result. So it seemed what actually happened was that my assumption that it's not possible to go beyond this limit, that was wrong. And that was very curious, because it was such a very simple assumption. And we were then very curious what the machine has actually done, what it really means that the machine has found to overcome this limit. And after a few days doodling around with the solution, we actually found that the machine has completely implicitly connected the generation of entanglement with an idea that has been investigated in the early 1990s by a quantum optics group from Leonhard Mandel that was never connected to entanglement research. The program had no idea about this. It didn't have any literature to learn from. It completely independently and implicitly came up with the idea to use this old technique in the context of entanglement generation. And that was extremely exciting because as soon as we understood what the machine was doing, we were immediately able to generalize it to many other cases. And we wrote a paper about it, and this paper was published in BRL, which is one of the top physics journals, just describing the idea and the generalization that the machine has found to solve this question. And if you look at the author list, that's one of the very rare cases where none of the co-authors actually invented the idea that is described in the paper. The idea was in some way implicitly invented just by the machine, and we as humans just needed to understand and generalize what it has done. So this idea, a little bit later, a few months later, we found out that actually this idea that we found can be best described with graph theory. So basically, the machine has shown us that there seems to be a weird hidden connection between quantum optics and graph theory. And as soon as we understood this, we had a very different way to think about quantum optics experiments. And just by hand, we were then able to think about new quantum interference effects, new sort of experiments that one can build that one would not think about otherwise. And a number of experiments have recently been implemented to show this connection between graph theory and quantum physics for the first time. I'll show some of the results that emerged just from this connection for the first time. For instance, these are two experiments that show some new type of quantum interference effect that can perfectly be described by this graph notation. And this is the so far largest integrated photonic circuit that has ever been published. And it is purely based on the representation on this graph-based representation that was inspired earlier by the solution of the machine. So I got asked several times whether we put our algorithm actually as a co-author, but we didn't. We put the name of the algorithm in the acknowledgement and said, thank you for analyzing 100 million of experimental setups, but that was it. But a little bit later, Zeilinger, my PhD supervisor, and I were invited to contribute to a perspective article about big ideas in science And we contributed one small chapter about how computer can automatically find new and surprising ideas or insights. And in this article, I was able to smuggle in my computer algorithm, so into the author list. So here, AI Melvin was the name of the algorithm. So here, co-author AI Melvin in a peer-reviewed journal. But the fun thing, what happened afterwards, is that two of the co-authors actually became Nobel Prize winners. So this is John Goodenough, Chemistry Nobel Prize in 2019, and this is Anton Zeilinger, my PhD supervisor, the Physics Nobel in 2022 for entanglement research. So now we have a paper where AI algorithm shares co-authorship with two Nobel Prize winners. Yeah. Okay, so this was already quite some time ago. These days we use quite different algorithms for designing quantum experiments. And actually what we are doing is we use exactly the link between quantum experiments and graph theory. So basically we have questions in quantum optics. We translate these questions into this very abstract space of graphs, and then solve the question in this abstract space and translate the solutions back into the concrete quantum optics space. And I can very briefly just give an intuition what this graph stands for. So here the vertices stand for the paths of the photon. So here there are four possible paths. The edges between two vertices stand for a two-photon correlation. So for instance, this is a correlation between a photon in A and a photon in B. Each of the edges are weighted, and the weight stands for the strength of that correlation. And the color stands for the photonic mode, for instance, for the color or for the polarization. So for the degree of freedom in which we are looking at the quantum correlation. So now what we are doing is, we know basically when we fix the number of paths, we know what is the most general experiment one can build. The most general experiment one can build in the lab is can be described by a complete graph where each of the edges is parametrized. So now we know that this thing, if we have all edges parametrized, represents every possible experiment I can build in a laboratory with four paths and within this techniques of quantum optics. So this graph stands for a quantum optics experiment. But even more, this graph contains the information about the quantum state, depending on the weights of the edges. So now we can write objective function, loss functions, just in terms of the weights of this graph. For instance, if you want to have a very high sensitivity quantum microscope, we would use Fisher information in terms of the weights of this graph. And then we have translated now the discrete problem of quantum optics, of how to set up an experiment, into a purely continuous problem. And continuous problem can, of course, be solved very similarly as you would solve, for instance, neural networks with gradient descent and with other techniques that have been invented for that. And here the cool thing is, we solve a problem, we solve this continuous parametrization. It gives a very large graph. We potentially want smaller graphs, smaller setups. So we prune the graph, we make it smaller, we optimize again, make it smaller, optimize again. And then usually we get a solution out that is very small and very interpretable and gives you actually already in some way the explanation why that experiment works. Recently we have expanded this not only to state generation, but also to the design of quantum gates and quantum measurements and quantum communication protocols. yeah, here are some highlights. I will maybe skip that specific example. Yeah, so now we have very efficient ways to design quantum experiments with this link to the abstract world of graphs. Let me come now to a different topic. So we were not only interested recently in quantum experiments, but we think that this method can be used in much more generality. For instance, to design new gravitational wave detectors. So gravitational waves are produced in some of the most extreme events in the universe. For instance, when two black holes collide or when a star explodes, then gravitational waves emerge. And those gravitational waves then go through space-time, and at some point they hit Earth. And when they hit Earth, they are extremely fine. So to observe them, you need incredible sensitive devices. And these are gravitational wave detectors. This is one example of a gravitational wave detector that stands in the US. It's built by the LIGO collaboration, and it's basically one laser and a bunch of very fancy optics that is split into two 4-kilometer arms. And when the gravitational wave hits now from above, then, for instance, this distance gets a little bit shorter, while this distance gets a little bit wider. And with advanced classical and a little bit quantum optics, you can actually observe this difference. So that is the outline. And usually what you want is that those detectors are very sensitive over a large range of frequencies. So this is the frequency of the gravitational wave, and you want the detector is very sensitive, and lower is higher sensitivity. So this detector is obviously, if you want to think about designing new detector, it's obviously, again, a very difficult discrete problem. You need to know where do you put your elements, and continuous problem. You need to know which parameters do those elements have. So we used the similar ideas before, and actually an idea that is also very much inspired from how neural networks work. So we, instead of solving this discrete continuous optimization problem, we embed this problem into a much larger space that is purely continuous. And then we can use, again, techniques that are known from neural networks. So we call this actually a universal, or let me say it differently. Neural networks are universal function approximators. What you are doing when you train a neural network is that you actually try to find one function that is encoded in this very large universal function approximator. We do here something similar. When we want to find a new gravitational wave detector, we want to find one configuration in this very large overcomplete system. And we can use exactly the same technique because everything is continuous. We can use gradient-based optimization techniques. And the cool thing is, if you just change some of the parameters, so for instance, here in the middle of these blocks, we have beam splitters, and the four things around, those are mirrors, and I can modify the parameters of those. And outside I have some light sources, lasers, and some quantum light. And just by changing the parameters, I can get the original solution that I showed on the slide before. I can get this solution to be encoded in the universal interferometer just by changing the parameters. So now the original solution, the best known solution to humanity, is inside. The question is, can we find better solutions? And we run our algorithms. We asked it to optimize for a number of different frequency regimes where one expects interesting astrophysical observations. And we found for each of those regimes, we found solutions that are significantly better than those that were designed by humans. And we also looked into some of the solutions, what they are actually doing, because we are not only interested in finding a better solution, we actually want to know if they are better than solutions that humans came up with. What did the machine find and what did the machine do that humans don't know yet? And in many of the cases, and some of the techniques that the machine was able to find have been discussed in the 80s and 90s in theory papers by the gravitational wave community. But many other techniques have never been discussed and seem completely alien to us. So we actually spent roughly 6 months trying to understand what is actually going on in those detectors. And we were by far not able to fully understand all of the ideas and tricks that the machine has used to build up those more sensitive detectors. So because of that, we published then a gravitational wave detector, SU, with 50 beyond human capability solutions that the gravitational wave community can investigate now. Yeah. So then maybe for the last 10 or 15 minutes, let me switch the topic. Let me talk about something at the bigger picture. So in general, we are not only interested in finding better solutions, but we want to actually get new scientific understanding from those programs. And at some point, when I was working in Toronto in Erlangen Aspuru-Guzik's research group, we were wondering how AI can contribute generally to scientific understanding. So our first problem was, what do we even mean when we talk about scientific understanding? So that was already the first strange roadblock. But then we found a book written by a philosopher, Henk Direct. The book is called Understanding Scientific Understanding. So that was exactly what we wanted to do. And that book got some big prizes in philosophy, the Lakatos Award for contributions in philosophy of science, one of the biggest prizes in philosophy. And Direct came up with some ideas how you can think about scientific understanding. So he says that scientists can understand the phenomena if they can recognize qualitative characteristic consequences without performing exact calculations. So basically, scientific understanding is connected to the skill to use concepts fruitfully without full computation. So that was a very important first part, that a crucial element here is the limitation of the computation. And then, okay, we have now this input from the philosophers who thought about this topic for decades. We wanted to get empirical examples. So we reached out to many computational physicists, biologists, chemists, and asked them for the personal anecdotes how they used AI themselves to come up with new ideas, with concrete new concepts, and with scientific understanding. And doing that, we got at least 50 answers. All of those answers are in the supplementary of our paper. They are partially extremely entertainingly written. So those answers and the input from the philosophy of science has helped us then to come up with a rough classification of how AI can help to get scientific understanding into 3 parts. Where the first one is computational microscope, where the machine can mimic real experiments that we cannot perform in the laboratory yet. And you can actually observe the whole trace, what is going on. The second class is AI as a resource of inspiration, where you get new ideas. This is one thing I find extremely interesting. And the third class is agent of understanding, where the AI understands itself and translates it to humans. And we did not get a single example for this class. And even until today, there's not a single example where I would say this definitely falls in class 3. So let me focus a little bit on the second class, the AI as a resource of inspiration. So one idea would be that AI can find anomalies by looking at different coordinate systems, and it shows you, okay, this is a point that seems very weird, you should look at it. And then a human can look at it and think about what this point actually means and why it doesn't fit with the other topics, with the other points. A different way is using a large amount of scientific literature to get new ideas. Of course, today with GPT, but there are many other techniques. And let me show you this as an example. So some years ago, we started to use hundreds of thousands of scientific papers. And the goal was to kind of suggest some interesting ideas. Okay, so that was difficult. But as the first thing, what we were able to do is to predict what scientists will do in the future by looking at how they behaved in the past. And how that could work is we used this number of papers and we generated a knowledge graph. It's basically a graph that consists of vertices and edges. The vertices stands for concepts, and the edges are drawn when a certain paper mentions these two concepts in the title or the abstract. So it's a very simple way to build up a knowledge graph. But it turned out already several years before in computational biology that you can do very powerful things with such semantic networks. So now, because we have the papers from the past, this knowledge graph evolves over time. And it gets larger and larger. And now you can use the information from the past to train neural networks to predict what will happen in the future. And that could work in this way. We take the data from 2017. We take two concepts that have never been investigated together and put this information into a neural network and ask the neural network, will these two concepts be connected in 5 years? But for 5 years, we have the answer, of course. 2022, we have the answer, so we can give a supervision signal. So we do this for millions of unconnected edges, unconnected vertex pairs. And by that, we train the neural network to estimate what will be done, what will not be done. And then, of course, when we finish training, we can put in the data from 2022 and estimate what will happen in 2027. Or today, we can put in the data from 2024 and estimate what will happen until 2029. It turns out you can actually get a very high prediction quality. So in some sense, for some questions, it even looks like the behavior of scientists is in some way nearly deterministically predictable, which is very crazy. Recently, we try to go a step further, not only predict what will be done, but also what that will be done will have a high impact. So basically, we ask two concepts that have never been investigated together. Will those two concepts, if there would be a paper about them, will that paper be of high impact or not high impact? And we can basically do exactly the same. We just have a more complex knowledge graph now, but we can again train a neural network to solve exactly that point. And one can also predict what will be impactful and what not to a very high degree of quality. Now, of course, we not only want to predict what will be interesting, but actually, what will be impactful, we actually want to produce interesting and potentially impactful suggestions. So we use this technique. One can use this technique and for a suggestion of research collaborations, for instance, for pairs of researchers. That works in the following way. You take researcher A, the researcher A The interest of researcher A is a subgraph of their entire knowledge graph. When you have researcher B, also the interest is a subgraph of the entire knowledge graph. Now you can look at which of the edges have never been connected before, and which of those could be of high impact. And now we can compute and rank, and then you have pairs of concepts, and then to produce practical ideas, we can use now language models, for instance, GPT, as an input of background of the scientist and background of the topics that we want the idea to be about, and ask it to generate ideas in that way. And we did this and asked actually more than 100 other research group leaders in the Max Planck Society in all fields of science and physics, bio, humanities, mathematics, CS, in all fields of science. And they helped us to evaluate their personalized research ideas. So those top-level researchers have helped us to get more than 4,000 or 4,500 research ideas evaluated by their interest level. And it's interesting that around 15 or 20% of those AI-generated ideas were actually ranked to be highly interesting. And the fun thing what we can do now is, because we have thousands of evaluations, we can actually use this technique to train a new machine learning model that can predict what scientists will find interesting and what not. So we can hopefully get the next generation of this tool to produce even more interesting research ideas. Yeah, I can skip this. So now then, just a few words on other possibilities to get new scientific understanding. One can use interpretable outputs of machine learning systems. For instance, mathematical formulas. There's a field, it's called symbolic regression, that can get very complicated formulas that describe the data, but those formulas are interpretable in a way, in the form that humans would read them. Yeah, and if you have formulas, of course, you can immediately interpret the physics that this formula is describing. Let's skip this. A different way would be to, instead of looking at the output of the model, look at the input of the model, look at the intrinsic states of the model and think about how the machine is thinking about a specific problem. And there have been very interesting questions. There have been very interesting results where researchers have seen that the machine actually finds the correct coordinate system to solve a problem, similar as we would do, especially in astrophysics, that the machine switches from geocentric coordinates to heliocentric coordinates and other interesting things. So there are techniques how to observe these intrinsic states and see really how the machine is thinking about those systems. Skip this. Another technique would be to observe the machine while it is exploring a very large space. That is related with curiosity-based exploration and intrinsic reward, an extremely interesting topic that I very much recommend to look into at some point. Okay, let me come to an end. I've shown that now we have algorithms that can perform, that can solve experimental questions or design new experiments in many different fields beyond what humans can do, especially for quantum optics. Now recently for gravitational wave optics, we have projects for microscopes and telescopes, and hopefully have soon new fancy quantum telescopes that can look at the sky. The great thing is we can not only find those solutions, we can also learn new concepts, new ideas from those solutions. What I've also shown is that it's possible potentially to use programs to generate personalized, new, high-impact, interesting research questions. This is very much at the beginning, but I guess this will be possible in the future. And one thing that I find extremely interesting is to think about what it really would mean if we want to build an artificial scientist. I think we need to very much understand first what makes a really good human scientist and what are the traits of really good human scientists. For instance, why is a human creative? What does it actually mean to be creative? Why is a human curious? There's intrinsic motivation to observe new things, to go into new directions, and so on. What does it mean that a human can understand something? And I think when we understand more about this, we can actually build really powerful artificial scientists. Okay, thank you.
Very much, Mario, for that fascinating talk. So we'll take some questions from the room first, and then if there's any questions online, as always, just raise your hand and I'll call on you or drop a message in the chat and I'll read out loud. So any questions from our students in the back?
Yeah, thank you for the interesting talk. I'm wondering if you're generating new ideas based on past data. Science in over the long term undergoes various paradigm shifts. I'm wondering if any kind of model will kind of like reinforce us getting stuck in a particular direction rather than thinking of it from a completely different model.
Yes. So for the second part, at the moment, we use only scientific literature. That means the answer is probably yes, that we are just trying to fill gaps and don't go into completely new directions. There's research how one could go into new directions even with this, but at the moment, I think we are trying to fill gaps. The point is that I think there are enormous gaps and you can also do interesting things there. But to go beyond, I think you need access to some grounding, and that works. That could work with tools. So tools in this case, we don't use any previous data. We try to use previous data, but actually it doesn't make too much sense to use previous data because we want to go far beyond of what humans have done. We want to find completely different ideas. So why would you even care about starting with human data? So all of the interesting things that we found started completely tabula rasa from scratch. The only thing that we had was the algorithm had access to a trustworthy physical simulator. Basically, it can run Schrödinger's equation, Maxwell's equation in the machine and know what would happen in the laboratory.
I had a question, which I guess would be an extra box to add on here. But I know that some people are doing this in fields like chemistry, which is to actually have like an automated researcher in the lab.
Yes.
Yeah, so there's a chemistry group here, for instance, who pioneered like a robotic arm that can move around a floor plan, monitor experiments as they're being undertaken, make adjustments, and then I think do some preliminary analysis of what data's coming in and make adjustments kind of based on that. If you're interested in that, that's going to be a talk that we'll have in May.
Okay. By who?
It's going to be by Jean-Francois, I forget his surname, but he's part of Andy Cooper's group.
Okay, yeah. Andy Cooper is one of the heroes in that field, yes.
Yeah.
That's a very good point. The chemists are a source of inspiration, and they are always ahead of us physicists, which is kind of weird as a physicist to think about that. But that is one of the reasons why I joined after my PhD a computational chemist group, the group of Aspuru-Guzik, because I've seen that they are so far ahead what is done with AI in general. than what is done in physics. And Erlangen is also one of the big shots with robotic experiment. It just got an enormously large grant from Canada, I think $200 million just to build fancy devices. I think Andy Cooper is also part of this. I've seen they work closely related. So yeah, this is extremely exciting, but expensive.
Oh, for sure. Yeah, for sure. I wonder if they'd be better or worse than people at designing quantum optics experiments. The level of kind of precision that you need.
Yeah. So there's some automation of experiments where you say everything what should be done, and then you can control. It's already quite some old with PID controllers. You can control it also. You can automatically align. But the level of completely setting up an empty optical table, that I haven't seen yet. But I wouldn't be surprised if one sees that soon. Yeah, just a question of money, I guess.
Yeah, it'd be an interesting proof of concept if you started off with like a very simple experiment and you just had a machine come up with an experiment design, and then it kind of has a different branch which then sets up the experiment, runs the experiment, analyzes the outputs, and presents that like a short journal article or something. Just as an initial starting point, that could be quite terrifying.
Yes, that would definitely be fantastic. Yes, I want to see that, definitely.
So we have a couple of questions online. So Bradley in the chat asks, how much of the code that you've talked about today is available online? Would it be possible to explore its applications to other research domains?
Yes, all of our codes are available on our group's GitHub website. Some of the codes are actually extremely well documented. For instance, the code about microscopes there we use. If you're interested in this topic, this is very, very future-looking, forward-looking. We use a language that's called checks. It's an auto-differentiable language that DeepMind has invented to train their neural networks. So it's a very young language. And the language is written a little bit more general that you can also code other stuff, not only neural networks. And here, for that specific application, Carla Rodriguez, who was the person in charge, she wrote a full optics simulator for high precision, super resolution microscopy in that checks language. And now we have speed ups of a factor of 10,000 or 15,000 compared to normal language. So that is a very well documented code on our GitHub repo. The quantum is also very well documented. The gravitational wave, I wrote the code, so it's not very well done, but soon there will be updates from my students with much better code. So all is available.
Yeah, it's interesting you should say that, because I was going to ask what kind of inspiration you took from something like AlphaZero, which learns to play chess and comes up with conventional techniques that people have developed over centuries playing chess, but then and then comes with new creativity, creative solutions.
But that's a good question. There is a fundamental difference between playing chess and playing Go versus designing experiments. Namely, for chess and Go, you need to build strategies. You have an opponent, you need to react to your opponent. So you need to build a strategy. And with this strategy, you solve a problem. While we don't need a strategy, we want to find a gravitational wave detector. So we can do the optimization directly, while in those reinforcement learning applications, they have to learn a strategy. And then via the strategy, you solve the question if you would apply it here. So that is much less efficient. We've applied this, and so far, these direct methods are significantly faster. But those direct methods, as I explained, they're very much inspired by how neural networks work, actually using the same languages, using the same principle, this thinking of this universal simulators, universal ansatz. They're much inspired, but there are also differences.
Very interesting. Okay, I can see John's got his hand up online.
Yep. I was just wondering, do these models account for like noise and errors in the actual experiment itself? Because in quantum computing, noise is quite a big problem. So I imagine a complex
Yeah.
system or solution it comes up with could actually not be realistic.
Oh, yes, yes. Yes, that is an important point when you develop your objective function, actually. So, for instance, for gravitational wave detectors, our first objective function was just getting getting a high sensitive detector. Then it found one, but we found out it's extremely not robust. And second, it would burn all of the optical equipment because it used such high laser power. So then you need to introduce, okay, it should not burn everything, obviously, shouldn't destroy anything. And you need to introduce noise sources. So basically, what happens if your parameters are not precise? What happens if they change every time a little bit? Should still give you a solution. So yeah, that's a very important point.
Thank you.
Yeah, we have another question in the chat from Artem. Artem thanks you for the talk and then asks, do you see physicists collaborating more closely with AI assistants or co-pilots in their daily work? I'd be curious to hear your perspective and how this might evolve in the next few years.
Yeah, I think some develop very fancy techniques. Some others don't care at all. So I know a lot of very good physicists, experimental physicists, for instance, they don't care at all about those techniques. Those techniques don't help them. Yeah, so I think it depends on the type. Yeah, I'm not sure. So I think especially in theoretical physics, because it doesn't need this difficult real world, much more will be possible to where clever programs can help and take more and more of the task that usual theoretical physicists would have done. In the experimental world, I think it's much more difficult. Yeah. One sees that there's a lot of progress in kind of the creative arts, but there's very few progress in robotics compared to what language models can do for writing and DALL-E can do for pictures and so I can do for videos.
Any last questions in the room? I was kind of wondering if, on this question of creativity, you'd had any thought as to what way where one finds creativity in scientists usually. I guess it tends to be among kind of younger researchers at the start of their careers, have some kind of creative ideas. They're not too embedded in the orthodoxy of the kind of the previous generation. So you don't necessarily see the same genius again and again and again over the course of a 40-year career, going up with multiple paradigm shifts. I was wondering if that's a question of there's some like inherent creativity like in like a younger mind, or if they're less bogged down in the data in which or the ideas in which they're living, or something else entirely. Yeah, I wonder if you thought about that and thought about how that could be implemented into your approach.
Yes. Creativity is one of the topics I'm thinking very much about, also with a number of other people, because we want to have our programs to produce much more creative things. So what you ask is a very important question. One of the points is, what do you mean by creativity? And there you can go again to philosophers and psychologists. They have criteria that might make sense, might not make sense for you, but they came up with a number of ways to think about that. And those criteria you could hopefully use to actually improve the creativity of your algorithms. I want to say something about younger people being more creative. There was a very interesting study, I think in Science, by a group of Albert Laszlo Barabashi, who has shown when you look at the top work of scientists, and look at, is it the first work, the second work, or the last work in your career? It is equally distributed. So your best work in your career could with equal probability be your first and your last. So it seems this idea of young people are more creative is not necessarily true. It's a nice way to think about, but when you look at the data, it's not true. What happens is that young people have more output. That maybe biases this question, but it's not that you have better ideas when you're young than when you're old.
That's interesting. I guess you could also take that same data and put it on an axis of how many years have they been active as opposed to their publication number. I guess you probably would see something similar.
I think when you take the number of years into account, then you have the bias that young people are more productive because later you, I don't know, you have family maybe and so on. You have other obligations. So they found that younger people are more productive. But if you get away with the age and just sort the paper number, then you see an equal distribution. It's an extremely fascinating paper, very highly recommended.
Yeah, I'll check it out for sure. Thank you. Yeah, I heard the definition. Somebody was trying to come up with a definition of genius once, like what it means to be a genius. I can't think of the source of it, but it was talking about how you'd rank somebody like Einstein against somebody like Stephen Hawking, for instance. What they came up with was, can you point to other researchers in the field who are working on similar things and probably would have come to the same conclusion given enough time? Like, were they only 2 or 3 years behind? Or was it just like, oh no, there was nobody else thinking about this, there was nobody else anywhere close to it, and
yes,
suddenly that this one singular person came on and pushed everything really forward. And I guess that's the one you'd want to. That's the thing that would be missing from the current approach. I guess the current approach would be, like you said, identifying the gaps in the current theory.
yes, that good that you mentioned it. There's one work I found is super fascinating by James Evans. So James Evans is a computational sociologist who investigates how scientists work, and he has found that that when you look not only at the idea level, that means the concept what have been done, but also at the individual level, what are people actually working on, you see spots where there are missing links and no person is there that can find it because no person is working in this direction. And then the machine, these ideas are much more surprising than ideas where there anyway people are working there. And then programs that can suggest such ideas might have an even higher impact.
Yeah, this is such interesting stuff. Like it's getting down to what the nature of science is, but then also having practical applications, which like normally I guess these are two completely different fields. Like you have these people don't talk to each other. Like, oh, the philosophy,
Yes,
you know, who cares what they're doing? You know, it's not relevant to my experiments. But with AI, it's linking together these areas really nicely.
yes.
That's super interesting. Well, thank you very much. Well,
Thank you very much for all of the questions and the interest.
yeah.
Bye.
So, we may or may not have a seminar in April. We're still trying to line something up for that, but if not, we'll see everyone back in May for a talk on autonomous chemistry. So thanks very much, Mario. Okay, see you later.